Hi friends, welcome to the lecture of linear algebra. In last lecture, we have seen what is a singular and non-singular linear transformation, and we have also seen what is a characteristic polynomial and characteristic equation of a matrix and some examples depending on this definition. Now today we have to see what is a similar matrices. Similar matrices. Two matrices A and B. Two matrices A and B are said to be similar if there exists a non-singular matrix, that is non-singular means invertible matrix. If there exists a non-singular, that is invertible matrix P such that B is equal to P inverse AP or A equal to P inverse B into if suppose we have given two matrices A and B, then when we say that the matrices A and B are similar matrices, if there exists one non-singular matrix P such that non-singular means its determinant is non-zero, and we know that every non-singular matrix is an invertible matrix. That is, if there exists a invertible matrix P such that this P can be written as P inverse AP or A can be written as P inverse BP, then we say that two matrices A and B are similar matrices. Now there is one result depending on this definition. Similar matrices have same characteristic polynomial. So here we have to show that if A and B are any two similar matrices, then we have to prove that the characteristic polynomial of these two matrices are same. Let A and B be true. Let A and B are two similar matrices. Okay? Similar matrices. As matrix A is similar to matrix B, then by definition of similar matrices, this B can be expressed as P inverse AP. And also given, and now we have to show that the characteristic polynomial of these two matrices are same. Let f of x and g of x be the characteristic polynomials of matrices A and B respectively. Matrices A and B respectively. And in previous lecture, we have seen that what is the characteristic polynomial of a matrix, any matrix A. That is, characteristic polynomial of any matrix is nothing but xi minus that matrix. First we have to take xi minus A, and if we find out the determinant of xi minus A, then the corresponding polynomial is a characteristic polynomial of matrix A. Okay, so as f of x is a characteristic polynomial of the matrix A, then f of x is nothing but determinant of xi minus A, which is from definition of characteristic polynomial, and g of x is nothing but determinant of xi minus matrix B. Now we have to show that these two characteristic polynomials are same, that is f of x equal to g of x. For that, consider B is equal to P inverse AP, which is from this one. B is nothing but P inverse AP, which implies xi minus B is nothing but x into I minus P inverse AP, where this I is the identity matrix of order. What is the identity matrix of order? Equal to order of matrix A. Okay, so which is nothing but xi minus b is nothing but P inverse of x into I into P minus of P inverse AP. As identity matrix is committed with any matrix and any scalar, then this xi into P is nothing but P into xi, and P into P inverse is 1. So actually this is nothing but this one. So, and which is nothing but P inverse xi minus A into, okay, which is nothing but P inverse xi P minus P inverse AP. Okay, this one is nothing but this one. Now take determinant of this equation, then we get determinant of xi minus b. Actually this equation is not equation, it is a product of matrices, and this one is one particular matrix. Then we have to take the determinant of both the matrices. Then determinant of xi minus b is nothing but determinant of P inverse into xi minus b into P, and we know that which is nothing but determinant of P inverse into determinant of xi minus b and into determinant of P, and which is from, since determinant of matrices A into B is nothing but determinant of A into determinant of B. As these three are the matrices, then determinant of P inverse into matrix xi minus b into matrix P is nothing but determinant of P inverse into determinant of xi minus b into determinant of P. Okay, so determinants of xi minus b is equal to determinant of P inverse into determinant of P into determinant of matrix xi minus b, and which is from determinant of A into determinant of B is equal to determinant of B into determinant of A. Okay. Now, which is nothing but again determinant of, from this determinant of A into determinant of B is nothing but determinant of A into B. Therefore, determinant of P inverse into determinant of P is nothing but determinant of P inverse into P into determinant of xi minus B. Now, P into P inverse is identity matrix. Therefore, determinant of identity matrix is always 1, and which is determinant of xi minus, which implies determinant of xi minus, sorry, which is determinant of xi minus p, sorry, determinant of xi minus a. Okay, determinant of xi minus b is nothing but determinant of xi minus a, and determinant of xi minus a is nothing but the characteristic polynomial of matrix A, and we have taken characteristic polynomial of matrix A is f of x, and determinant of xi minus b is nothing but the characteristic polynomial of matrix B, and which is nothing but g of x, which implies g of x is equal to f of x. Therefore, the characteristic polynomial of the matrices A and B are equal. Therefore, from this we say that similar matrices have same characteristic polynomial, and that is we have to do, and hence the proof. Okay, now The next definition is characteristic polynomial of a linear operator. In last lecture, we have seen what is the characteristic polynomial of a matrix A. Now we have to see what is the characteristic polynomial of a operator. Polynomial of a operator. Let T be a linear operator on n-dimensional vector space V. Dimensional vector space V over space V over field F. Okay, the characteristic polynomial of T is the characteristic polynomial of any matrix A which represents operator T in some ordered basis, V for vector space. So, what is the characteristic polynomial of a linear operator T? If we have to find out the characteristic polynomial of a linear operator T, then we have to find out the characteristic polynomial of a matrix A which represents the linear operator T in some ordered basis V for a vector space V. And we know that the characteristic polynomial of a matrix A which represents the linear operator T is nothing but the characteristic polynomial of a linear operator T. So here, to find out the characteristic polynomial of any linear operator, we have to first find out the characteristic polynomial of a matrix A which represents the matrix T with some ordered basis, in some ordered basis beta for vector space V, and which is the required characteristic polynomial of linear operator T. Okay. There are some notes. First one, the characteristic values of linear operator T are the roots of the characteristic polynomial. Okay. So if we find out the characteristic value of a linear operator T, then we have to find out the characteristic polynomial of operator T, and the roots of that polynomial is nothing but the characteristic values of the linear operator T. Second one, the operator T have at most n distinct eigenvalues. As we have taken T be a linear operator on n-dimensional vector space. As its dimension is n, then the corresponding characteristic polynomial is of degree n, and we know that any polynomial of degree n have at most n different roots. So the linear operator which is defined on n-dimensional vector space has at most n distinct eigenvalues. Third one is the operator T may or may not have the characteristic values. So if we take an operator T, then the operator T may or may not have eigenvalues, that is the characteristic values. It depends on the field. It depends on the field F. Okay. Let's take one example. If T be a linear operator on vector space R2 over R, which is represented in some ordered basis, by the matrix A equal to 0, -1, 1, 0. If suppose T be any linear operator which is defined on vector space R2 over R onto R2 over R, and which is represented in some ordered basis by the matrix. This is the matrix which is obtained with respect to ordered basis B. Then we know that if we have given one matrix, then the characteristic polynomial of that matrix is nothing but determinant of xi minus that matrix. So characteristic polynomial and characteristic equation is nothing but the characteristic polynomial will be equal to 0. Then the corresponding polynomial equal to 0 is nothing but the characteristic equation of that matrix. So characteristic equation of matrix A is determinant of xi minus A is equal to 0. So xi minus A, find out first xi minus A. Xi minus A is nothing but yes 0 0 yes minus A 0 minus 1 1 0. And which is nothing but xi minus A is equal to yes 1 minus 1 0 minus 1 minus 1 and x minus 0 again. Now determinant of xi minus A equal to determinant x square minus into minus plus 1. Okay. Now this is the characteristic equation, and this is the characteristic polynomial, which implies determinant of xi minus A equal to x square plus 1 equal to 0 is a characteristic equation of matrix A, which implies f of x equal to x square plus 1 and which is equal to 0. Now this polynomial x square plus 1 has no real root. This polynomial, its roots are I and minus I. If we put I x equal to 1, then I square is minus 1 plus 1 will be equal to 0, and if we put minus I, then again it is minus 1 plus 1 will be equal to 0. So this polynomial, as it is a 2-degree polynomial, then it has a 2 roots, I and minus I. So this polynomial has no real roots, since I and minus I are imaginary numbers. No real roots. As they have no real roots and T be a linear operator which is defined on vector space R2 over R, it means field is R, and our definition of characteristic value of a linear operator says that these eigenvalues or characteristic values must be a members of field F, since any C belonging to F is called a characteristic value if there exists some non-zero vector alpha belonging to V, such that T of alpha will be equal to C alpha. But here C is not a member of field F, then these are not the eigenvalues of linear operator T, which implies that T has no eigenvalues or characteristic values over vector space R2 over R. But if we take T be a linear operator from C2 over C onto C2 over C, and which is represented by the matrix A, and which is represented by matrix C. So DB a linear operator which is from vector space C2 over C onto C2 over C, and which is represented by matrix A, and characteristic polynomial of matrix A is x square plus 1, and it has two eigenvalues I and minus I. As here the field is C, then the eigenvalues I and minus I are belonging to this C. So the linear operator T has two eigenvalues which are I and minus I, which implies T has two eigenvalues or characteristic values I and minus I. Hence, the operator T may or may not have eigenvalues, and which is depending on the field F. As here field is R and eigenvalues are I and minus I, and which are not belonging to R2 over R. Therefore, the operator T has no eigenvalue. But if we take this field as a C or C2 over C, then the eigenvalues I and minus are the members of the field C. Therefore, the linear operator T has eigenvalues. Hence, we say that the operator T may or may not have eigenvalues. Okay. Now, the next point is annihilating polynomial. Annihilating polynomial of operator T. Okay. First, we have to see what is the annihilating polynomial of a linear operator T. Let T be a linear operator on finite dimensional vector space V over the field F, and let f of x is any polynomial over field F If f of t is equal to 0, then we say that polynomial f of x, polynomial fx annihilates the linear operator annihilates t. So, what is the analytic polynomial for a operator T? So, if suppose we have given one operator T, which is defined on a finite dimensional vector space V over the field F, and fx be any polynomial over the field F, then if f of t is equal to 0, then we say that this polynomial f of x annihilates the operator T. Okay. Now, similarly, we have to see what is the annihilating polynomial of a matrix. Okay, let A be a square matrix of order n over the field F of order n over F, and let f of x is any polynomial over F polynomial over field F. Okay, if f of a is equal to 0, then we say that the polynomial f of x annihilates annihilates the matrix A. Matrix A. So actually, the characteristic polynomial, in next. Actually, the characteristic polynomials of linear operator T and the characteristic polynomial of a matrix A are the same things. Okay. Now, if suppose A be any square matrix of order n over the field F and Fx is any polynomial over the field F, and if suppose f of A is equal to 0, where the 0 is a null matrix of order n, null matrix of order n. Okay. Then we say that the corresponding polynomial f of x annihilates the matrix A. Okay. Now next one is, what is a monic polynomial? Okay. Now the polynomial in x, the polynomial in x over the field f, over the field f is called monic polynomial. Monic polynomial if the coefficient of highest power of x is 1. So we have to see what is a monic polynomial. The polynomial in variable x over the field f is called a monic polynomial if the coefficient of highest power of this variable x is 1. That is, for example, if suppose f of x is equal to an x raised to n plus an minus 1 x raised to n minus 1 plus up to so on a1 x plus a0 is a given polynomial in x of degree n. Then this polynomial is said to be a monic polynomial if the coefficient of highest power of x, and here n is the highest power of that x, so which is will be equal to 1, that is an equal to 1. If f of x equal to an x raised to n plus an minus 1 x raised to n minus 1 plus up to so on a1x plus a0, then if an is equal to 1, then the corresponding polynomial f of x is said to be a monic polynomial. Now let us see what is a minimal polynomial. Again we have to see what is a minimal polynomial of a linear operator and what is the minimal polynomial of a matrix E. Minimal polynomial of a linear operator. Let P be a linear operator on finite dimensional vector space V over the field F, the monic polynomial of lowest degree over the field F over the field F that annihilates operator T is called minimal polynomial for T. polynomial or linear operator. So, if T be any linear operator which is defined on a finite dimensional vector space V over the field yeah, then the monic polynomial and we know that what is a monic polynomial? Monic polynomial is nothing but it is the polynomial in X over the field here is called monic polynomial if the coefficient of highest power of that x is 1 and such a monic polynomial of lowest degree over the field here that annihilates the linear operator t is called the minimal polynomial of operator t. Polynomial for t or polynomial of linear operator t. Now we have to see what is a minimal polynomial of a matrix. Again, let A be a square matrix. Let A be a square matrix of order n over the field F over the field F. Then the monic polynomial of lowest degree over the field F over the field F that annihilates the matrix A is called minimal polynomial of matrix A. Minimal polynomial of A. Okay? So if A be any square matrix which is of order n over the field F and then the monic polynomial of lowest degree over the field F which annihilates the matrix A is called the minimal polynomial of A. Annihilates of matrix A is nothing but the analytic polynomial and we have already seen what is the analytic polynomial of linear operator and what is the analytic polynomial of a matrix. Now if f of x is any minimal polynomial of linear operator T or of matrix A. Actually, the minimal polynomial of a linear operator T and the minimal polynomial of operator A, and the matrix A which represents the matrix Q with respect to some ordered basis. Then the minimal polynomial of linear operator T and the minimal polynomial of matrix A are the same things. Okay. Now, then if fx is a minimal polynomial of linear operator T or it is of A, then first one fx is a monic polynomial. Every minimal polynomial is a monic polynomial. Second one, f of x annihilates T or A. If fx is minimal polynomial of matrix A, then it annihilates the matrix A. And if fx is minimal polynomial of linear operator T, then it annihilates the linear operator T. And third one is no polynomial over field F of degree less than the degree of Fs annihilates T or E. Okay? If, as we know that minimal polynomial is nothing but it is the monic polynomial of lowest degree which annihilates the matrix A. As fx is the minimal polynomial of a matrix, then there is no polynomial of degree less than the degree of fx which annihilates the matrix A. Okay, this is from the definition of minimal polynomial. Now we have to prove one result, that is the minimal polynomial of a matrix is unique. So here we have to prove that if we take a minimal polynomial of any matrix A, then it is a unique. Let the minimal polynomial of matrix A is of degree R. So if A be any square matrix of order something n, then we have to prove that the minimal polynomial of that matrix is a unique. And if there is a minimal polynomial, then the polynomial have some degree. Let us suppose that the minimal polynomial have degree R, and let f of x equal to x raised to r plus a1 x raised to r minus 1 plus a2 x raised to r minus 2 plus up to so on ar minus 1 into x plus ar, and g of x is equal to x raised to r plus b1 x raised to r minus 1 plus b2 x raised to r minus 2 plus up to so on br minus 1 x plus br are any two polynomials, are any two minimal polynomials, are any two minimal polynomials of matrix A. So here we have to prove that the minimal polynomial of a matrix A is unique. If possible, suppose that there are two minimal polynomials of a matrix A and which are f of x and g of x, and we have already assumed that minimal polynomial of a matrix A is of degree R. Therefore, fx and gx are two minimal polynomials of degree R. As each minimal polynomial of a matrix A is of degree R, then there is no polynomial of degree less than R unless the matrix A, which is from the definition of analytic polynomial and minimal polynomial, which implies there is no polynomial of degree less than R, annihilates the matrix A, annihilates the matrix A. Okay, as here fx and gx are two minimal polynomials, as f of x and g of x are minimal polynomial, then fx and gx annihilates the matrix A, which implies f of A is equal to 0 and g of A is equal to 0. Therefore, from equation 1 and equation 2, we get from 1 and 2, f of A is nothing but f of A is equal to a to the power r plus a1 a to the power r minus 1 plus up to so on ar minus 1 e to the power a plus a naught I is equal to 0. This is equation 3, and f of g of A is equal to a to the power r plus b1 e to the power r minus 1 plus up to so on gr minus 1 a plus b naught I is equal to 0. This is the equation 4. Now, subtracting equation 3 from 4, we get subtracting 3 from 4, we get this AR minus AR is 0, and B1 a to the power R minus 1 minus A1 a to the power R minus 1, which is nothing but B1 minus A1 a to the power R minus 1 plus B2 minus A2 a to the power R minus 2 plus up to so on br minus 1 minus ar minus 1 a plus b naught minus a naught into I is equal to 0. So here we get one polynomial which is of degree r minus n, r minus 1, and which annihilates the matrix A. So here we get one polynomial of degree less than r, or degree r minus 1 and which is less than r, and which annihilates the matrix A, which annihilates means if we put the matrix A, then the corresponding value will be equal to 0. Annihilates A, then which is contradiction to the definition of minimal polynomial, since we have assumed that the minimal polynomial of matrix A have degree r, but here we get one polynomial which have degree r minus 1 and which annihilates the matrix A. So this is not possible. Hence this polynomial must be a zero polynomial, which implies which is a zero polynomial, then only it is possible, which is zero polynomial. And if it is a zero polynomial, then its coefficient must be equal to 0. That is b1 minus a1 equal to 0, b2 minus a2 equal to 0, and up to so on. br minus ar is equal to 0. Sorry, here is let's take AR, BR, whatever it is. Here is BR and BR. Actually, there is no need to take 0 at BR minus AR will be equal to 0. As B1 minus A1 will be equal to 0, then B1 must be equal to A1, B2 equal to A2, and up to so on. BR is equal to AR. Now put these values in polynomial f of x and g of x. If we put b1 equal to a1 is equal to b1, a2 equal to b2, ar minus 1 equal to br minus 1, ar equal to br, therefore these two polynomials are actually the same polynomials, which implies f of x is equal to g of x. So here, if we consider there are two polynomials of a matrix A, then and if we have proved here that these two polynomials are already the same polynomials, which implies then from this we conclude that the minimal polynomial of a matrix is unique. Polynomial of matrix A is unique. A is unique, and which is the required. Okay, thank you for watching the lecture.